A little test of it. What? Okay.
Testing, test.这样就可以。
I'm good.
Welcome to the second Q lecture of 2023, and Andrei is going to continue to talk about the special functions.
Thanks, YP. Thanks to all of you who came back, and well, is it sound okay? So we'll just continue with what we discussed before. So somehow we just go through the slides as I prepared them. So we started talking about the Q gamma function, and which is this infinite product, and we discussed why it's really a Q analog of the ordinary gamma function. And so we got to this point here. So if it was a finite product, like so, if it was a finite, some finitely many terms like that, that would be the trace of a diagonal matrix, or trace of matrix with eigenvalues Z1 through Zn acting on the space of polynomials on some vector space. But Q gamma function is an infinite product, so that means we have to act on an infinite dimensional space. And these letters Q and Z in general, so far so enumerative geometry starts the answers being more or less integers. And then now if we want something to have a function, there's some letters, some variables in the function like Q and Z. For us, currently there is only one scenario where you can get a variable like Q and Z that has to be just an element in some group. And so Q and Z are somehow not related in any way. So just each of them is an element in GL1. So each of them is an invertible number. And these two copies of GL1 have to act on infinite dimensional space, so that the character of this action, well, maybe I wrote the character on the dual space, so this is Z, Q squared Z, and so forth. And so what is this infinite dimensional space M? Well, it's just a space of polynomials. If you want to compute the sort of character, it doesn't really matter if you view your functions as functions on the space of polynomials or the space of formal power series. It doesn't really matter. And so you have an infinite dimensional vector space, which is either a space of all polynomials or all formal power series. It's spanned by its basis is given by. So these are the spaces of maps from a line to a line. Its basis is given by 1, x squared, and so forth, countably many basis vectors. And since it's a map from a line to a line, then I have automorphisms of the source line and automorphisms of the target line act on the space of maps. And how do they act? So they by precomposing with the factor and postcomposing with the factor. So the way I define this is precomposes with factor Q inverse and postcomposes with the factor Q inverse. And that has the effect that on the monomial x to the k, this x will the weight Z inverse Q to the minus k. And so then on the dual space, it will be Z times Q to the k. And so we get our space, which is, so again, a modular space M is just a space of maps from line to line, or you can say maps from, like a formal. So people say there's formal disk, like a formal power series in one variable. So it's back for formal disk to a line, and that's an infinite dimensional vector space bound by monomials. And if I consider the action on the functions on this infinite dimensional vector space, I'm gonna get the Q gamma function. That was where we ended up last time. And so that's where from this point we'll continue. But anything which I didn't repeat enough times? But it's okay to learn things with multiplicity somehow. It helps. So in the similar way, in principle, you can study maps from M-dimensional space to N-dimensional space, and so that would be given by so if you're doing from M-dimensional space to N-dimensional space, it will be N tuple of polynomials or formal power series in M variables. And this N and M somehow this plays a different role, because if I have more than one variable in the source, I'm getting things. So maybe I'll just show you a picture. So if I'm, so here in the first scenario, I'm going from my source is two-dimensional and scaled by two functions, Q1 and Q2. And then my target is one-dimensional scaled by Z. Then the character of what I'm going to go, well, I missed the inverse here. I apologize. There should be another inverse here. So then I have to take all possible monomials in two variables, and that will have this sort of effect. And this is things like this people call double gamma function, which you can also write as an infinite product of ordinary Q gamma functions. Whereas by contrast, if I'm going from a line to two lines, and my source is here scaled by just one variable Q, and the target is scaled by two variables Z1 and Z2, then we'll just have a pair of polynomials. And so my character is just a product of a pair of polynomials. Then the character vector space is tensor product of two things, and the character is a product of the things. So you just get the product of things like this are very interesting. We're not going to talk about them. We will talk about this. And this is the basic feature here is that if I'm studying map from let's call it formal disk, or so that means I study formal power series. So if I'm studying maps to two-dimensional space, it will just factor over the coordinates. And in general, if I study maps from this thing to a product of two, so I can study maps to manifold and another manifold. And if I study maps to a product of two manifold, this will factor. So this sort of things, function of a manifold, which is additive under cisjoint union and multiplicative under product, these are usually called genus. And so in principle, so like in generalizing this, you can study maps from this formal disk to any kind of manifold you want, and this you'll have the character of all functions. So this would be in the manifold, you may or may not, in the target, you may or may not have an action, but in the source, since you're going from in your source, you always still have this action Q. And so on this space, so M is now, so I apologize, this should be straight M. Now that I look at the big screen, I see every typo I made very clearly. So this should be this kind of M here. And so this is, so on this space, I still have an action of Q, and then I have a well-defined character, which you can compute if you know how to operate with Chern roots of tangent bundle. And this is like it defines, first of all, it defines a genus. And I want to make two remarks, not that I'm going to use them a lot, but a kind of interesting remark. I don't know, maybe important remarks, is that one of this is of course just Q analog of something called the Iritani genus. And second, it's directly analogous to the fact that if instead of doing formal power series, I did a formal Laurent series, that would be very closely related to elliptic genera of your map. So this you can somehow if you that would be a very clear. If instead, so maybe I go back here. If instead of, or maybe even here. So if I had to continue this also to negative monomials, that would be essentially an elliptic function, some sort of elliptic genus. And so this gamma Q genus, that's maybe the first building block in any kind of enumerative theory, because anytime you're going to map something to some manifold, the first thing you can always start try taking your map and expanding in a Taylor series. So that would be the first ingredient of any kind of so this is the first building block in any kind of theory of maps from curves. And
did you just say that
yeah. Yeah, it's like half of elliptic genus. Yeah. Yeah. We'll see elliptic stuff later in this lectures. So probably tomorrow. But this is for those of you familiar with elliptic genus, it's like a half of elliptic.
Somehow it has an advantage.
I believe it has an advantage. It's an object, right? So you can somehow I don't say that it very naturally comes up in enumerative theory just because it's like the first thing you can ever consider. So if you wanna study maps from some curve somewhere, you can always start by studying problem log, take your map and expand it in Taylor series. So the first thing you're going to see is that sort of thing. Okay. So I want to say one fact, which we'll come back to this maybe next lecture, is that in general, so in what I was trying to say, in general, people like to study maps from like a Riemann surface from a complete algebraic curve. But there's always there's very fruitful interplay in enumerative geometry between local and global things. And here, so far by local, I mean that one can study maps from formal discriminates. You study formal power series valued in some manifold, or you can go be slightly more global. You can study maps from a line. And also, still I would consider to be a local thing is that if you study maps from projective line, but you impose the condition that somehow nothing happens at infinity. No, somehow things are constant at infinity. Like for those of you in mathematical physics, you sort of very often we study things, like in a space, but then you can, well, I don't know, but you can imagine that this things that happens in the space, it really happens on some kind of compactification of a space, but with the condition that nothing's going on at infinity. That's and in all of these setups, you have an action, very important, you have an action of Q, which scales your source. All of these sources have an automorphism Q. And you get something which depends on that Q. And global means we want to pass from this information to something where we now move from a different general curve, may not have an automorphism, but somehow there's some ways to pass from this information to global information. I would consider one example of success of this given Talt-Telemann theory that tells you some particular enumerative problem you can solve in one particular way going from local to global. So and I'd like to compare, this is tangential to the subject of this lecture, but one subject in which special functions really come up in these days. Like, this is the if you think about like classical special functions, something, I don't know, classical orthogonal polynomials. So I mean they've been progressing in mathematics, their use is kind of progressing from some area to some other area, and they used to be that people who really study mathematical physics, like problem electricity and magnetism, that would be very, very proficient with classical special functions. Then kind of representation theorists took over, and they became like the kings of the special functions. For instance, here you can have so we were talking about mapping. We will in a second we'll be talking about something mapping to something to P1, and maybe more generally, you can think of, instead of mapping something to P1, counting sections of some P1 bundle over your curve. So you have some non-trivial P1 bundle, you want to count sections. So if you do this over a finite field, that's by definition Eisenstein series for PGL2. So by definition, if you want to somehow count, the Eisenstein series for PGL2 is counting sections of some bundle for PGL2 over the field of functions of that curve. And the field of function on an algebraic curve defined maybe over a finite field, then that's an example of a global field, and another example of a global field is something like rations, and counting direct kind of Eisenstein series for PGL2 over rationals. That's just asking, you think that's a very different pictures, counting vectors in a lattice, and counting sections of a P1 bundle, but in fact, they're both really counting points of your P1. So here, if you're counting vectors in a lattice, that they're parameterized by rationals. So you're counting points in P1 over your field, maybe with some weight. So then you weight the vector. So in an Eisenstein series, you weight the vector by the length of the vector raised to some negative power. So, and here you weight it by, here the direct analog of that is just the degree of section. So the kind of problems that we're doing, they're not far at all removed from the kind of computation people do it in number theoretic computations. And there, of course, it's the principle that you can express some global information in terms of local contribution is sort of, very, very basic. You have some formulas which really combine a local contribution into this sort of counts. And what maybe at this point we'll maybe not talk more about this, but what can notice, and one can try to describe it maybe in more some kind of zero level later, is that these local number theoretic contributions, the limits of the things the things we compute, we take two different limits in them. We get the things that so for instance, this kind of, when we talk about maps to P1, maybe in a half an hour or tomorrow, we'll talk about maps to P1 in our sense, counting maps to P1. We'll see that the local contribution we get, well, they're some kind of McDonald polynomials. And then you can take two different limits. You can take that variable q to 1, or you can take that variable q to 0. And you'll see the things that correspond to Eisenstein series at Archimedean and Archimedean places. And in terms of what we've already seen, we've seen the Q gamma function, but the Q gamma function, so if you do this procedure, if you send Q to 1 in Q gamma function, you get the gamma function. If you send Q to 0 in the gamma function, you just get, so in the Q gamma function, if you set Q to 0, you just get one factor like so. And so this is, and this is, you think, well, where did I see this? Well, of course, you see this in the product, which is a zeta function of a field. So this would be so completed zeta function over, say, over the integers. That will be a product of all primes, and this will be this contribution for a prime, and which is completely analogous to just the first term in this Q gamma function. So if you set Q to 0, that just only that first term survives, gives you that, and then there will be a contribution like so. And the reason there's S over 2 is because the Archimedean, somehow you want to think, imagine yourself what the Archimedean point looks like. It's not really a formal, it's not really a disk, not really a formal disk, like a half of the formal disk. It's like a cone with angle pi, not 2 pi, because it's a real point, not a complex point. You take factors of complex by that bar, so you get something with comp. Anyway, so this is, let's go to the next section. And so this is Pochhammer symbol is something discussed, but in this section we'll maybe make our first step towards something which is actually not a local situation, slightly global, just a little bit global. And okay, so this Pochhammer symbol, that Z sub D, this is just this people sometimes in the additive notation, people sometimes say factorial power. So because an additive notation will be like x plus 1, x plus 2, and so forth, people say it's a factorial power. And in general, in ours, it's like so, it's a ratio of two gamma functions. So this is an object that appears in every page on every book on special functions in its additive form. And of course, what we already know, we talked about, this is like a truncation of Q gamma function. You take a product for Q gamma function, and you truncate it over up to Z plus 1 terms. And so this is the same. So we talked about how the Q gamma function is supposed to be characters of functions on the space of all polynomials. Now, if you take just the polynomials of degree d, there will be a finite dimensional space. So we're going from more complicated to less complicated. Take the ratio of two gamma functions. We just have polynomials of degree d, finite dimensional vector space, has functions m as polynomials of degree d. Functions on it will have this character. And what's global about it is because polynomials, you can say the polynomials of vector space of polynomials of degree d. Well, that is the section of a line bundle on P1. So on P1, I have an interesting line bundle, and I count sections. Well, what's the line bundle? The line bundle consists of all possible functions that have a pole of order at most d at infinity. That's my line bundle. Okay. That's so again 1 over this Pahammer symbol is the character of this finite dimensional vector space where formed by sections of d on P1. And maybe think about it slightly more geometrically, this space of section of O of d on P1, this is also, just by definition, it's the space of deformation. If I put P1 inside the total, so a line bundle is a collection of lines for every point on P1. So the total space of a line bundle defines for me a surface. And if I put my curve as a zero section in the surface, then the space of deformation, well, it's just that is the space of section of this line bundle. So this is this is space modular space M. That's the space of deformation of that zero section inside the surface. And I don't know if this is confusing or illuminating, but I've drawn here this bucket to illustrate the idea that this is a curve in a surface with a positive normal bundle. For those of you familiar with toric geometry, when we draw like a toric picture of something, then if the normal bundle is positive, that means the angle is acute, and when normal bundle is negative, that means the angle is obtuse. And if you somehow want if you want maybe maybe a symbolic representation of a positive or negative normal bundle, well, we can think of this as a rim of a bucket. I don't know. In Taiwan, the buckets are straight, or they like this. Both. So in Russia, buckets are like that. So and so if you take the top rim of the bucket that can deform, that has since the angle is acute, this can deform. And then in a second, we'll talk about the bottom. Then, of course, then the normal bundle is negative. That cannot deform. Anyway, so there's a geometric picture that goes with it. If I have this moduli space M, I can consider as deformation of a curve in a surface, where the surface it's a line bundle over that original curve. So that's for every point there is a line. And if I want to move the curve, means I have to find a section of that line bundle, and this would be so the character of functions on this modular space is at 1 over Pahammer, right? Okay. And that kind of the fact that there's a ratio to gamma function makes total sense, because how do we describe the sections of this line bundle? We decided the line bundle is formed by functions with pole of order at most d at infinity. So if we want to specify what does it mean to be a section, well, we have a function. We extract the terms of degree d and higher from this function. This would be a function. I can take the polar terms at infinity, so it can take the terms of d plus 1 and higher, so there will be a map. And M is, by definition, the kernel of that map. And so if I want to, but this is, well, in this case, this happens to be, all of these are linear spaces. And if I want to know the characters of functions on these linear spaces, well, I can take the functions here, divide by functions there, and this will give me this ratio of gamma functions. But so now with that, so now that we've beaten to death this elementary, so maybe, you know, I apologize if those of you who are waiting for real special functions to appear, that you may be bored to death by this gamma function manipulation, but maybe it's okay to spend time on them. So now we have this formula, which is a ratio of two gamma function is the character of functions on the moduli space we want to consider. Anytime you have a formula which is in which you can plug in numbers outside of the domain somehow we derived some formula in some with some, you know, we consider some geometric situation in the dissections of this. We took some polar terms here, something like that, and then so we derived this formula. But in this in this formula, we can plug in d to be d here is supposed to be, but we think of this as kind of positive number. But in fact, you know, this formula makes sense also when d is negative. And what will be happen if d is negative? So if I have a function and I'd like to extract, and I take coefficients of this expansion at infinity, starting with some negative terms. So I'm looking for polynomials of negative degree. Well, there's not many polynomials of negative degree except 0, which is kind of degree minus infinity if you want. And so if d is negative, our actual moduli space reduces to 0. There's just nothing, not only the 0 polynomial will have all these terms, all terms. So you're asking for also the negative terms at the expansion at infinity to vanish. And that means your polynomial has to not have a pole of some order at infinity, but have vanished to some order at infinity. And you know, there's no such, just 0. But in fact, this map here previously was surjective, but now it will miss all the negative terms because there's just, if you take a polynomial, expand it in the series infinity, there's no way you're going to get negative terms here. So it'll miss, them will miss. And so, which is reflected to the fact that that if I take this ratio, instead of being 1 over something, it in fact now becomes a polynomial. So it becomes, instead of going in denominator, it goes in the numerator. And the way to interpret is that in this map, where we previously, our moduli space previously was the zero-sky homology of my line bundle, and now it's just reduced to 0. Instead, I'm getting a co-kernel here. So this map misses something, gets a co-kernel here, and that's the first homology of my line bundle. And this is the trace of this alternating sum of exterior powers on here. So that's, you should, you know, something also we discussed here before. So this is the trace of this alternating powers of that. And the moral is that if I want a formula, if I want good count, so how do you know you have a good count setup for your counting theory? Means you have a good formula which is valid in all cases. Like, you know, business theory is valid for you know, you don't have to consider separate cases. It's just always valid. And so similarly here, if you want a theory in which this sort of formula is true whether d is positive or negative, then you should not just worry about the moduli space M, but also worry about all equations that define it, including maybe those that satisfy it identically. It means if the sum equation is satisfied identically, that is geometric somehow. That's a generalization of situation. Then when you sort of you impose an equation, but in fact it's automatically true. There's co-kernel here. And so if you have that, that means you have to have well, I don't know. I think I've beaten this slide to death. I think maybe I can move to the next slide. But this geometrically, the formula that if d is negative, that instead of going in denominator, it goes into numerator, that corresponds to the fact that if I have a normal bundle negative, that not only the curve does not deform, but in fact it has non-trivial abstraction. There's some vector space, namely this H1, that prevents the curve from being able to go up this bucket, and this type of product exactly measures how much the smaller the d, the more and more abstracted this is, and so you get more and more terms for more and more abstractions. Anyway, I tried to with the bucket analogy, I tried to explain the rudiments of the theory of virtual structure shifts. Okay, I hope Jonas survives this. Well, anyway, so if you account, so moral of that, if you count things correctly, means you account for all variables in all the equations, even when the equation is somehow, even when the system is overdetermined, then you get better formulas, and somehow then you get formulas which are both better. You get setup which is better geometrically, and it's also better, just leads to better formulas. Okay, so that's all right. Finally, we got to like a actual first special function, the hypergeometric function. So what is so maybe the general shape was classical a hypergeometric function. Well, there are many definitions of what it means to be a hypergeometric function, but more or less the hypergeometric function is some series, could be univariate, could be multivariate, in which you have a series. Well, here series is indexed by one integer d, and all terms in the series are either some powers of some variables raised to that power d, and the rest are some Pohammer symbols d. So that's, and that could be could be more terms, could be more variables, but it's general thing. It's like every term is some. It doesn't have to have the same. It doesn't have to have the same number of Pohammer symbols upstairs and downstairs. All you need to know is every term is some Q gamma over Q gamma, and so this every term gives you some sort of product of Q gamma over Q gamma. So there's some bunch of Pohammer symbols, and then there's a monomial. But we want to look at this specific one because it's maybe we don't. Well, I mean, one has to focus on something, and so we'll focus on this one. And to explain what's so nice about this function, and okay, so maybe I'll say it depends on it involves three variables, and then variables. This Q over T here is just for comparison with something else. Of course, I might as well redefine Z, bring this QT over T into Z at something that doesn't matter. But what's important here is that the numerators can exactly mirror denominators, where in denominators I have Q's, and in the numerator I have some other variable T. And before talking about this particular function, maybe I should talk about its classical kind of ancestor. And here comes an interesting fact that if you want reasonable formulas, somehow something one can actually read, people usually denote by the same Pohammer symbol, both the Pohammer symbol and its Q analog. So I apologize for it, but it only happened here in this formula. So classically, if you consider a Q, if you say ordinary gamma function over gamma function, that is also denoted the same way. But so maybe it's only in this line this has this different notation. And so classical analog is the same. So this is Q becomes, we discuss Q, it's 1. Product becomes plus, and alpha stands for A and tau stands for T. Otherwise this. And this is the function that for special values of parameter reduces to things like Gegenbauer polynomial, also known as the something called spherical functions. And what is a spherical function? So if I have an n-dimensional sphere, then classically people study eigenfunctions of Laplace operator on this n-dimensional sphere. for instance, if you want to say something about the Laplace equation on in the space in polar coordinates, you'll get a part of that. Part of the Laplace operator on flat space will be in polar coordinate Laplace operator in the sphere. So if you want some kind of separation of variables, you want probably plug in an eigenfunction of Laplace operator on a sphere. Among all these eigenfunctions can be, in fact, all these eigenfunctions can be expressed via hypergeometric function, but the ones we want to study right now are the ones that depend only on the distance from the North Pole. So only, and the distance is convenient to measure in angle, so it's an angle, maybe call it theta, that goes from 0 to pi. And what one can should do is one can, the data of an n-dimensional sphere, and you have the eigenfunction, there'll be countless linear eigenfunctions. So you have n one parameter, it runs from 1, 2, 3, and so forth. And then you have a number k, runs from 0, 1, 2, 3, and so forth. And what you need to do is you have to set alpha plus tau to be k. That makes the previous, maybe I will go to this. So if this number is a negative integer, then this series terminates. So if number is a negative integer, this is a polynomial. And so if I set, so I made a mistake here, so it should be minus this number should be k. Oh, right. This is, I've written here this correctly. So this is which means that series will terminate after k steps. And then my z, I put the exponential, roughly the exponential of tau, of I tau. And for tau, I have to put some expression that depends on. So it's kind of remarkable that all these functions in which involve two discrete parameters, namely dimension of a sphere and the number of the harmonic, they in fact, there's one function of some number of variables in which you plug some discrete values to find your eigenfunction. And so this is how you get all these things. And one can notice, so that maybe to somehow boost our familiarity with this function, one should note that there must be two special cases, namely the one-dimensional sphere and the three-dimensional sphere are groups, and functions. So in the three-dimensional sphere, functions that are invariant under, so functions that depend only on the angular distance, those are the functions that depend only on the conjugacy class of the matrix. So if you're asking on a group, you're asking which are the eigenfunctions of Laplace operator that depends only on the conjugacy class, those are the characters. And so it has to be the case that we should, when n is like 1 or 3, which means tau is either 0 or 1, then we should see the characters of S1 and S3 as groups. And sure enough, so if I look at this formula, if tau is 0, then this whole thing terminates after one term, and you get just this monomial, so which is the character of S1. So characters of S1 are monomials. And if tau is 1, then this whole thing cancels, and you just get it. Every term gets with, so tau is 1 means this term cancels with this term cancels with this term, and then you get a sum, just a sum of monomials, which is the character for the group S3. Okay. So now we go back to our Q difference world, and the now maybe let's go back here. So if I want, so this zonal spherical functions were happening when the series terminates, when this number is a negative integer. Similarly, you can make this series terminate. And so this terminating cases I've written some of them out. So if I take A to be this combination. So these are in fact nothing but McDonald polynomials for the simplest. So McDonald defined his multivariate orthogonal polynomials. Well, I mean, they're McDonald polynomials, of course, somehow it's just this hugely important contribution of McDonald, but also contribution of other mathematicians. And anyhow, they're defined for any root system. And of all root systems, the simplest one is called A1. And if you think of a sphere, sphere is a manifold which happens to be a symmetric space. And all symmetric spaces have some data attached to them, which begin with the root system. And the root system for the sphere is that A1. And so what are the McDonald polynomials? How did McDonald think about, why did he consider this polynomials? So you should maybe I should make it clear that McDonald polynomials are defined for any root system, and therefore any root system, there are countless many of them, they get very, very complicated, which is why, beautiful but complicated. And so I don't know, you may or may not appreciate the complexity of these objects by taking the simplest root system and the first terms, but anyhow, somehow you maybe get some flavor of what this stuff might look like. He was thinking he previously in maybe some 20 years before introducing McDonald polynomials, he solved the problem which may be seemingly unrelated, namely there are p-adic, so sphere is a symmetric space, and there's a p-adic analog of symmetric space, namely, for instance, the simplest thing you can take SL2 over p-adic and mod out by its maximal compact subgroup. This is direct analog if I take the same thing real. So if I take SL2 real and mod out by maximal compact subgroup, I'm getting the Lobachevsky plane, or the upper half plane, which is a symmetric space dual to the two-dimensional sphere. And so this is a p-adic symmetric space. And on the p-adic symmetric space, we also have, so for instance, so for when this is with p is equal to, this quotient here is just the infinite binary tree. So this like a combinatorial analog of the upper half plane. So if you think of upper half plane as being like a prototypical hyperbolic thing, the combinatorial analog of a hyperbolic two-dimensional thing is an infinite tree. And P enters as this would be infinite ternary tree. So T plus every vertex has T plus one neighbors. And so similarly, this p-adic symmetric space has a Laplace operator, just as any kind of tree, means the value of the Laplace. So you want to what does Laplace operator do? It adds, or maybe takes the average of all of values at all neighbors. So Laplace operator, you value the vertex. You look at here, every vertex has 3 neighbors. You have your function, you sum up the values at three neighbors. And so then you can ask, what are then the analog of this zonal spherical function? You can ask for what are they. So here I had a distinguished point, and I looked for eigenfunctions that depend only on the distance from the distinguished point. The analogous thing here, I want an eigenfunction that depend only on the distance from my chosen point. Doesn't mean the tree is homogeneous, doesn't mean which point I choose, but so let's choose this one. And so then you're asking, well, how many, what are the eigenfunctions of Laplace operators that depend only on the distance? And so, this problem has McDonald solved this in general for general p-adic symmetric space. And what the solution look like? So previously we had, when we talked about spherical functions on a sphere, there was a discrete parameter came from the fact that we have a compact space, the eigenfunction of Laplace operator are discrete, there are countably many eigenfunctions of Laplace operator. Here my space is like upper half plane. The spectrum of Laplace operator is continuous. However, the distance is discrete. So the distance takes only discrete values. Distance takes values only 0, 1, 2, 3. So to get so you need a function of one continuous, one discrete variable, and also of p. And what you do, you take McDonald's polynomial, you set q to 0. This is what we discussed. So usually you think of p as some power of q, and now slightly counterintuitively, if you talk about this kind of q analogs, then when you talk about a p-adic thing, then the first thing you have to do is to set q to 0. So you set q to 0, but then however t you set to t the p inverse. And then k, which was the number of the polynomial, that becomes the distance. K is the distance from the root vertex. And z, which is a continuous variable, labels the eigenvalue. So the z, so this maybe more symmetrically, this combination z1 half, z minus half, that thing is an eigenvalue of Laplace operator. And already here we see a kind of funny thing that what was the label here the label k was the number of the harmonic, and z was exponential of, well, was kind of like the z was exponential of I times the angle. So the argument of McDonald polynomial was the coordinate, and k was the label. Here, k is the coordinate, and z is the label of the harmonic. That's already kind of disinteresting. So from this things you can, from the slide maybe you can remember 3 things. First is that McDonald polynomials, and then later in life McDonald realized that in fact he can define polynomials that specialize to both p-adic and real symmetric spaces. That's what I was going to say. Oh, right. I forgot. Why is T kind of like P? Why T plays the role of P? T was previously playing the role of the dimension of the sphere. What is the dimension of the sphere? What's the importance of the dimension of the sphere? The importance of dimension of the sphere tells you how much mass do I have at the so this, if I want to write my Laplace operator on a sphere in radial coordinates, then what I need to know is how much mass do I have at a fixed distance. So the bigger dimension of the sphere, the more somehow the more mass I have. Well, it depends. I mean, goes as some powers has to do with the dimension. And similarly, P controls, since I have regular P plus value 3, P controls how much mass I have at the given distance. So, right. Okay, so slightly advanced slide. Maybe we'll go through it quickly. Similarly to what we discussed similar to what we talked about, the 3-sphere. Similarly for McDonald polynomial, the analog of 3-sphere for McDonald polynomial is the case when Q equals T, in which case all fraction cancel. I get this sort of thing, which is kind of like the character of SL2. And in general, McDonald, maybe one of the best ways to view McDonald polynomials also geometrically is in fact, this is something. So okay, this may be remark some of you may appreciate, but maybe most of you can just ignore. But that there's in modern representation theory, there's a very interesting thing called QQ characters. And maybe if there's a question, maybe I'll come back to it later. But some funny thing you can, if you have a geometric realization of some representation, you may want to enrich the character slightly and have something called a QQ character, maybe slightly dramatically, maybe. And for McDonald polynomials, well, in this case, definitely in general, what it ought to be is that this series is in fact a QQ character in this sense for representation of SL2. Maybe we'll come back to that if there's a question. And so the kind of, maybe, let's go back here. So here I stress, maybe I overpedal this thing, but maybe I'll stress again that here the argument of McDonald polynomial was the actual coordinate in the space, and the label was the label of the index of the eigenfunction. Here the roles are reversed. The argument in space is the label, and the distance space is the label, and the argument is the label. Well, reversed. What's remarkable is, in general, there's a label argument symmetry in general McDonald polynomials, but in particular in this McDonald polynomial. So if you normalize them correctly, and this normalization involves some Q gamma functions for which there's also some explanation. So if you normalize them correctly, namely by their value at t, but this normalization is something explicit, something which generalizes also has a geometric meaning, and but would specialize to Gauss's formula. Then with such normalization, this thing is symmetric inside the label and the argument. In fact, the label and the argument play exactly symmetric. And this symmetry is really key to many formulas. Like, for instance, if you take any formula for McDonald polynomials, like McDonald polynomial, for instance, is given by some sum, right? We just by definition with some sum there. If you apply the symmetry, it already says something interesting. And if McDonald polynomial is also an eigenfunction of some difference operator, that's how it was constructed originally, if you apply the symmetry, it says how to multiply McDonald polynomial by some function, and so on and so forth. So it implies a kind of a really long list of formulas. And somehow ultimately these lectures are about how normative geometry provides, in fact, many functions with that kind of symmetry. But we'll get there. And so this as shown by Chen-Jung, was originally conjectured by McDonald. The same kind of evaluation and symmetry holds for general root systems. And classically, it generalizes. So this is what does it generalizes? One thing that generalizes classically, what does it says for GL1? So this is McDonald polynomials required for any group. So what does it say for GL1? For GL1, it says this. Okay, so maybe it's not so particularly exciting. But now when you think how the characters, what the Weil character formula, how does Weil character formula build a character of some group from monomials? Well, it'll have some summation over Weil group. The Weil group for the group and the dual group is the same. And so if you think about this thing, then you see that the properly normalized characters, irreducible characters for a group and a dual group are the same as function of two dual lattices. So if you have a character in a group, it lives, its argument lies in the weight lattice, and you put by considering things like that, you make another argument live on a co-weight lattice. And so you have a function on two dual lattices, and you exchange them, it becomes the same thing. All right, so, and another thing is that while in general, if I take a non-terminating case of McDonald polynomials, this is not symmetric. And that will be important. This is, if you take a non-terminating case, that is not symmetric. But it does prove that, it's easy to see elementary, can be argued in many different ways, that any expression like so solves some Q difference equation in every variable that you can see here. So that solves you have some expression like this, that any variable that appears here, there'll be some Q difference equation. And it's, Q difference equation with rational coefficient. So if I have a Q difference equation with rational coefficient, then of course, something like this is, so if I have, the equality, the terminating case, that certainly is a risky dense set of points. So if I have some symmetry that holds for the risky dense set of points, then it holds, that means the difference equation. So while this function is not symmetric, the difference equation that satisfies in Z and A are the same difference equations. That makes sense? up to some whatever normalization required. It's the same difference equation in the variable a and the variable z. And the solution, while the solution, this particular solution is not symmetric, so it's an interesting thing. So it's a function which is not symmetric in these two variables, kind of important, will be important. But maybe more importantly, that in fact the equation that is satisfied is symmetric in two. Oh no. Yeah, I don't know if I want to start a new section. Well, let's try to start a new section and then we can somehow continue. Let's see. So this is maybe let's start a new section and then we'll. So let's just do 2 slides in this section. So now, of course, the title of the lecture is Numerative Geometry and Special Function. We had this lengthy discussion of the special function. Now, it's reasonable to ask what is the meaning in a numerative geometry. And so let's look first at denominator. In every expression, the denominator is usually much more robust than the numerator. So let's look at denominator first. And so what is it? So first of all, we have 2 Pohammer symbols here in denominator. So we decided that each Pohammer symbol is the trace of something acting on function on the space of polynomials of degree d. And we also discussed that when I have products of things, that means products of the corresponding counts. And so if I have a product of 2 Pohammer symbols, maybe, so this product of 2 Pohammer symbols, that is the character of, again, a pair of Q and A, pair of things in GL1, acting in a certain way on the functions. Now I have 2 pairs of polynomials of degree. If I want, so 1 Pohammer symbol means polynomials, 2 Pohammer symbols means 2 polynomials. So, and how I'm going to think about this space of polynomials. So one way to think about it is like this. If I study 2 pairs of polynomials of degree less than d, well, let me put x to the d in front of one of them. And then this defines for me a map. So if I have a pair of, so one polynomial, and so the reason I put this x to the d, then since I can fix this coefficient of x to the d to be 1, I might as well consider this thing to be up to somehow. First put a non-zero coefficient and then consider it up to a multiple. So a pair of polynomials considered up to a multiple, it's a map. So a map, a point in projective line in P1, a point in projective line is a pair of numbers up to a multiple. So a pair of polynomials up to a multiple is a map to P1. And this is a map with, so to speak, quotes, because if I really want a point in projective space, it has to be the case that these polynomials don't have common zeros, because if I have 0 over 0 is not a valid point in projective space. But these are, it's okay. It's okay to allow these things. And in this particular instance, you can imagine that every time these guys have a common 0, that in fact, this somehow takes all possible values. So then you can imagine that the graph of this function, if it had common 0, then I put all possible values. But in general, you have to do something else. But here, maybe you can visualize it. And the condition that I put x to the d in the first factor means at infinity, I'm hitting the point 1 and 0. So I'm studying. So the denominator of this expression is the character of functions on the space of kind of maps from P1 to P1 that are allowed to have certain singularities and take values 0 at infinity. And maybe that's all that we have time for today. We'll start with the numerator tomorrow.
Are there any questions, Andrei?
I'm doing research on spherical code. So like you mentioned about the Gegenbar polynomial. So we know a finite set on a sphere, you evaluate on the inner product value on Gegenbar polynomial, some of that will be non-negative. And so I just wondering, do you know anything about this kind of generation to Euclidean space or some non-compact space?
Sounds like a complex equation. Maybe we sort of kind of complicated question. Maybe we can discuss it.
Okay.
Slightly, yeah, I don't know. Sounds.
Any other questions? Right. If not, then thanks.
Nobody asked about QQ characters. Okay. That's good. That's good. That's good.
Yeah. So anyway, so tomorrow it's going to be a grand conclusion of this year.
Grand conclusion. No,
Yeah.
no, no. No, Mikey, stop setting me up. You first.
I will set the expectation very high.
No, please don't.
All right. I'll see you tomorrow.
Many